So 14.3, we were discussing the Pythagorean Theorem last time, and we had done one example, although it was quite lengthy, where we were talking about this particular triangle, and it was made up of 3 different right triangles, and we found all their sides. One of the things we found in the midst of doing that is that we had a lot of similarities, so there were similar triangles in there that we were able to use. We're going to move on to problem number 2. Here it is. And it wants to know, can the numbers 10, 24, and 16 represent lengths of the sides of a right triangle? So what would I need to do to test whether or not this is possibly, or whether these numbers are possibly the lengths of a right triangle? Let me ask the question first this way. If these are lengths of the right triangle, which one of these numbers is the hypotenuse? 24. How come, Taylor? It's the biggest. You're exactly right. So if this is a right triangle, 24 would have to be, of those 3 numbers, 24 would have to be the hypotenuse. So if we were to set it up in that formula to test where would the 24 go? It would be on the c squared. So it would be 24 squared over here. So what would we do with a and b? Right. So we would let them equal the 10 and the 16. And now, it's a good idea for me to put a question mark here. I don't know that they're equal. Actually, that's what I'm trying to test and see, right? So 10 squared is 100. What's 16 squared? What'd you get? 256. Okay, so somebody tell me what 24 squared is. What is it? 576. Okay, so if I simplify the left-hand side, what do I get? 356. So, what do you think? No, these aren't equal, right? So because these aren't equal, what can I say? Right, this is not the sides of a right triangle. It could still be a triangle. One of the facts to decide if it's just a triangle would be to look at whether or not 2 of the sides added together is more than the 3rd side. We've talked about the fact that if you want to get somewhere, the shortest way to get there is to go in a straight line, right? So any other way that we go, say if I do this like that, it's going to take longer. So the 2 sides here and here would have to add up to more than the 3rd one. And that actually works. 10 and 16 would be 26. So 26 would be more than the 24. So these would form a triangle, just not a right triangle. Right? All right, we're going to talk about some specific types of triangles next. 2 of them in particular. One is a 45-45-90 right triangle. This triangle would be isosceles. In general, an isosceles right triangle with legs of length A have a hypotenuse of length A square root of 2. So what this is describing on your picture over here is that if you have a 1 here and a 1 here, and you were to use the Pythagorean theorem, 1 squared is 1, and then I'd have 1 squared plus 1 squared, well that's 1 plus 1 is 2. So the side C would have to be square root of 2. Right? That would actually satisfy the Pythagorean theorem. And that's fine, but there's really nothing special about it being 1, 1, and square root of 2. What happens is that if I had, let's say, 4 and 4 here, then this would be 4 square root of 2. If I had 7, it'd be 7 and 7 and 7 square root of 2. That's the relationship as long as you have a 45-45-90 triangle. Okay, special to that kind of triangle. There's another special triangle, and that's a 30-60-90 triangle. In this triangle, we actually have half of an equilateral triangle. I mean, that's one way to think about it. So in general, a 30-60-90 triangle, the length of the hypotenuse, which would be the 2's on the sides, are twice as long as the base. because it's equilateral, so it's half along on the bottom there. So they're in a ratio already of 1 to 2. And again, if you put those into the Pythagorean theorem, what's going to happen on this third side is that you would have the square root of 3. Okay, because 1 squared plus the square root of 3 squared would be 4. And that's 2 squared. Let me write that down. Does everybody see that okay? That's where it's coming from. I'm not going to ask you to generate that, but I want you to realize it's not just sort of appearing out of the middle of nowhere. It's all going back to the formula from Pythagoras, okay? Now, when I work with these kinds of triangles and I'm trying to find these specific lengths, these ratios can be quite useful. And we can also find other pieces of information once we have these triangles. In particular, we've been working with area. So if we're taking a look at this triangle, which is an equilateral triangle, how do I know that? Yeah, they marked all the sides with S. Everybody see that okay? And if I wanted to find the area of this triangle, what is my formula for the area of a triangle? 1/2 the base times the height. But in this particular triangle, what's the base? It's S. So that's good. What's the height? Well, it's not marked, right? I mean, that's the answer truly at the moment. I don't know. It doesn't say what the height is. But because it's an equilateral triangle, it's actually going to fit into this particular picture. So think with me. This piece is S. How long is this piece that I've marked in red? Half of S. We're pretty good with that. This is 1/2 S. And I should be able to find this piece right here by taking the shortest side. Which of those three sides is the shortest side? The 1/2 S, right? I mean, I only got 2 to pick from. It's either S or 1/2 S. 1/2 S is my shortest side. And over here it says that I would need to multiply it by square root of 3. So the height here is the 1/2 of the S, and then I'd multiply that by square root of 3. So in particular, what I have is I have that my height is square root of 3. That's almost unreadable. Let me change that to a little bit thinner. Square root of 3 over 2 times S. Or you could write it as S square root of 3 over 2, if you like. You can leave it written like this piece with square root of 3 after it. It doesn't make any difference, but that's my height. So when I'm doing my height over here now, I can use that value in there for it. So my height is square root of 3 over 2S. And I should be able to use these pieces now, multiply them together, and find the area of an equilateral triangle. So obviously I've got the S's here, so what's S times S? S squared. What am I going to do with the square root of 3 over 2 and the 1/2? What would those become when they're multiplied? Yeah, it'd be square root of 3 over 4. Does that make sense to everyone? Multiply across the top, 1 in the square root of 3, multiply across the bottom, I get the 4. This would be the area formula of an equilateral triangle. So that'd be kind of cool. If you knew that and you were now told, well, what's the area of an equilateral triangle that has side lengths of 10? You just plug 10 in for us, right? Just like the original formula for the area of a regular triangle up here, just any triangle in general anyway, allows you to plug values in. So does this one for the side length of S. All right, I want to introduce you to another formula. It's not really new, but it looks different. It's called the distance formula. Imagine you've seen it many times, but just as a reminder, the distance between the points A and B, if A is x1, y1, and B is x2, y2, is given by AB equals the square root of x1 minus x2 squared plus y1 minus y2 squared. Now, I'd like to just put them on my screen to show you what this looks like if I have 2 points. Say they're there. So we'll call this bottom point A, and it's x1, y1. And we'll call this top point B, and it's x2, y2. When I subtract x1 minus x2, what I'm really finding, like really and truly, is I'm finding this length right here. Because this right here represents x1's distance from wherever we started, and this represents the distance x2. So this side length right here is actually, how do I write it there? x1 minus x2. That's the length of that side. It's absolute values, so don't freak out on me there for that, but one way or another, that value is going to be positive. x1 minus x2 or x2 minus x1. And then this distance right here would be the same thing with the y's. This distance is y1 minus y2. And we've talked many a time now about the fact that the shortest distance between 2 points is a straight line. So that length right there would actually create a right triangle. And the right triangle says I should be able to square each of my sides and then take the square root. But that's exactly what you see right here. That's where it's coming from. So the distance formula is not really something special. It's just an application of the Pythagorean Theorem, or a different way of thinking about the Pythagorean Theorem. They're intimately related. However, it does express things very nicely. I mean, like I have places to plug in certain values if I've been given points, like ordered pairs, which is what I'm given on the next example. I have 2 ordered pairs, and I'm supposed to find the distance. Now, the only caveat when you're doing this is making sure that you're pairing the numbers up correctly. It doesn't really matter what order you subtract them in, because you're going to square them. So if I have the 2 and the 6, it doesn't matter. You can write 2 minus 6, I can write 6 minus 2, we're going to do the same thing. But the 6 and the 2 go together because they're both x values. And then the 5 and the 8 get paired up. So remember the plus sign in between. Again, I'm going to write 5 minus 8. By all means, write 8 minus 5 if you prefer, because we're going to square them. So as I'm looking at this now, I have 2 minus 6, which is technically negative 4. But what happens when I square negative 4? What do I get? Positive 16. It becomes a 16. What about the 5 minus 8 or the 8 minus 5? How far are those apart? 3. And 3 squared would be 9. What's the square root of 16? I'm sorry, what's 16 plus 9? 25. And the square root of 25 would be 5. And of course, that's the very first triangle in our story that Pythagoras comes across as working for the sides of a right triangle. Okay, fix my notes. The next question is actually a little more complicated. It asks for the perimeter of a triangle with certain vertices. So in order to do this, if you want to draw a picture, you can. But you've got 3 vertices, and it's a triangle, which all of that means you're going to have 3 sides, right? So in a very real sense, it's actually doing what we did on number 4 3 times. I need to find 3 side lengths. Is everybody cool with that? So the 3 side lengths are taking the ordered pairs 2 at a time. So I'm going to have one of them that takes A and B, one of them that takes B and C, and one of them that takes A and C. I'm going to find 3 lengths. And they can all be found with the Pythagorean Theorem. Now, lovely enough, one of our sides, or vertices is 0, 0. I like zeros. Those are nice to work with. So on the first one, when we take A and B and we compare them, we're going to have the square root of, and I have negative 4 minus 0. I think I need to write that underneath. Squared. And I have negative 3 minus 0 squared with addition between them. So obviously subtracting 0, that's a friendly thing to subtract. I've really here got 4 squared. That's 16. We did that a minute ago. And I've got 3 squared. That's 9. So what's 16 plus 9? 25. And again, the square root of 25 would be 5. Now, lest you think that these answers always work out perfectly, the next one won't. Okay, so let's check it out. BC. All right, so with BC, we're now going to consider side B and side C. Don't have nearly as many zeros as I had on the last one. So I have a square root. Somebody tell me what I'm going to write next. Excellent. So many negatives, right, Taylor? Yeah. Negative 4 minus negative 5. Whoops. All of that squared. And then what's the other piece?
Negative 3 minus 0 squared.
Yep. Plus negative 3 minus 0 squared. All right, so what is the difference between negative 5 and negative 4? What does that first value actually be? What is equal before I square it? How far apart on the number line are negative 5 and negative 4? They're 1, right? So if you think about it from a number line perspective, I think that's probably the easiest perspective on that one. Or you're welcome to do actually the addition for it. And the other one is actually 3 squared. So what is 1 squared? 1, and 3 squared is 9. So this is square root of 10, which is not a perfect square. Now grab your calculator. Let's go ahead and get a decimal approximation with, I think if I had us, let's get a decimal approximation for it. We'll give our answers in actual values and decimal approximations. That way you've got either way to do it if you're looking at your directions. What's approximately 10 going to be equal to? It's got to be 3 point something. 3.16. And 2 decimals is a good place to go, so 3.16. Okay, so we'll use both of these values in a moment. Our last one is AC. So we're considering the point A with the point C. This one's the easiest one to find. Because there's 3 zeros, that's helpful. It's always helpful. So one of them is actually negative 5 minus 0, and the other one is 0. I mean, there's all zeros. So what happens when I square negative 5? 25, and then the square root of 25 is 5. So this one ends up being a whole number again. So the perimeter, if we work with all of the numbers, exact representations, would be 5, square root of 10, and 5. So it would be actually 10 plus square root 10. Or if we use approximations, we would have 5 plus 3.16, and that would be approximately what? If I added, wow, that was from last class. If I add this number, the approximation here, and this one, what do I get? Yep, 13.16. Okay, so whatever your directions tell you, use that set of directions, approximations, or exact values. Another variation of the Pythagorean theorem is actually the equation of a circle. So suppose that we have a point xy on a point of a circle with a center at the origin 0, 0 and a radius of r. Then the general equation of the circle is actually x squared plus y squared equals r squared. And again, that looks an awful lot like a squared plus b squared equals c squared, right? Yeah. So in other words, if you notice over here, if you take this particular point, xy, it's got a length here of y and a width here of x, and you've got a Pythagorean, you've got a right triangle involved. So x squared plus y squared equals r squared, which is the radius of the circle. Now, that works great if the circle is centered at the origin. But if you take the circle and you shift it up, down, left, or right, just like we've moved other things in the past, it shifts it as well just a little bit. So on this one, you actually have to find the distance back to the center if the center is at, say, hk. So h being the x-coordinate, k being the y-coordinate, then x minus h squared plus y minus k squared is equal to r squared. And that kind of looks like the equation for the distance formula, right? x1 minus x2 squared. Yeah, they're all the same. There's just different letters showing up, but this is the same thing. So our last two examples are going to be talking about equations of circles. This one says to find the equation of the circle with center -3, 2 and radius square root of 5. So the second formula that I gave you, this one, is the one that applies when your center is not 0, 0. So our basic or general formula for this would be x minus h squared plus y minus k squared equals r squared. Now, one thing I'd like to draw your attention to is, do you see right here the negatives are a part of the formula? So if you have a positive coordinate for your circle over here, like the 2, when I put that in, it's actually going to say y minus 2, because k is 2. But what's it going to say for the x minus h part? It's actually going to become a plus, because I have minus and negative, right? If I literally plugged it in as x minus, and then I plugged in the -3 like that, I'd have two negatives, so I would get the positive. So this is actually x plus 3 squared. What is r? It's the square root of 5. So on the right-hand side, when I have the square root of 5 squared, I would actually get 5. So this would be the equation of my circle after I simplify some of those pieces just a little bit. And of course I can go the other direction. I can start with the equation and I should be able to use it to identify the center and the radius. So what is the center of this circle? What is the radius? Jot down what you think they are and then we'll check to make sure that everybody has the right items written down. Write down what you believe the center to be and what you believe the radius to be. What did you guys decide the center was? Remember, the center's an ordered pair. What does it look like from the formula? -3, 0. That's right, Rachel. So the sign switches, right? Whoops. Trying to go for this one. It says plus 3, but it's the opposite value of that, just like we had to do that over here, right? So I end up with a -3 for x, and then here, there's nothing beside the y. So it must have been 0. Very good. What is the radius? Someone else for the radius. 4. Why is it 4 and not, say, 16, Sabrina?
Because you squared the radius in the formula, so now you have to
Right.
square it.
Right. In the formula itself, the radius is squared. So if we've got the formula, we're going to have to go backwards and square root that value to give us, in this case, the 16, becoming a 4 for the radius. Any questions on those? All right.